Hello and welcome to this presentation on applying and sharing pre-trained BERT models for named entity recognition and classification in Swedish electronic patient records. The paper is written by me and Professor Hercules Talianis, who is part of the clinical text mining group at the Department of Computer and System Sciences at Stockholm University. In this talk, I will be speaking about named entity recognition and classification in electronic patient records, why it's of interest, and what previous results exist. Then I will talk about how we can use BERT models for this task. And finally, I will present our experiments and results. So advancements in technology in recent years have made it possible to use large amounts of electronic patient records to assist physicians and medical researchers in a number of tasks, for example, detecting early symptoms of disorders and predicting effects of treatments. However, the free text in these electronic patient records contains information which can be used to identify individuals. This includes the patient, but also any other individual that might be mentioned in the text. And so before the records can be released for secondary use, they first need to be de-identified. An important part of automating this de-identification process, which of course can be quite time costly to do manually, is named entity recognition and classification, which means detecting named entities in text and also categorizing them. At Stockholm University, we've been working with a research infrastructure called HealthBank. It contains a large number of electronic patient records from the Karolinska University Hospital. There have been some efforts in annotating parts of this data, which has resulted in Stockholm EPR-PHI corpus. This is a data set manually annotated with 9 named entity classes, or what we call protected health information classes. You can see here in the table to the right what these classes are. As you see, this is not a very large data set, and also there is a significant class imbalance in the data. This is an example of a record from the data set. In this record, we have replaced the named entities with surrogates, and we've translated it to English. But as you can see, there is information in this record that can identify not only the patient, but also family members of the patient. Also, we can see that there is some difficult language in this record, like abbreviations, short sentences, not always grammatically correct sentences, and some medical terms that are not common in everyday language. So these are just some of the difficulties in working with this type of data, as well as, of course, having limited amounts of label data. So my colleagues at Stockholm University have previously conducted some studies on this data set. They've tried training a conditional random field model and an LSTM neural network to solve this task. They've also applied these methods on a pseudonymized version of this data set. So by pseudonymization here, we mean replacing the named entities with the lexical surrogates. And so a benefit of having a model trained on pseudonymized data rather than authentic data is that if we are interested in releasing this model, releasing a model, in some cases the risk for breaches in privacy can be reduced if the model hasn't actually seen authentic patient records. Here we can see the best results previously reported on this data set. The highest precision reported is achieved using a CRF model. It's about 94%. However, at that point, the recall was significantly lower, and in a de-identification system, the recall is really of highest priority because the biggest risk with this type of system is that we might miss some sensitive information which could be used to reveal a person's identity. And so we're working towards minimizing the number of false negatives. So we made some attempts at improving recall by using resampling methods on the dataset. This was quite successful, but it came at the cost of decrease in precision, which, although it isn't the main focus of the identification system, precision still remains important if we want to maintain the usability of this data, so if we don't want to obscure the data too much. And here in the bottom table, you can see the best results achieved when training these models on the pseudonymized data and then attempting to make predictions on real authentic data. As you can see, these results are much more poor than when we've trained on real data. So we've been interested in finding a way to keep recall high without sacrificing precision, and also optimally to be able to train a model on these pseudonymized records while still being able to reach good results on authentic records. And we've been looking into BERT models. So there are some BERT models which are pre-trained specifically for the biomedical and clinical text domains, and these have shown to perform pretty well on this task, but for English electronic patient records. So far there's no such model for Swedish. In Spanish, there are some results on fine-tuning a multilingual BERT model for this task, name, density recognition, and classification in Spanish electronic patient records, and this has been quite successful with a reported recall of 93%. So far, however, no such experiments have been conducted on Swedish, as far as we know. And then in 2020, the Swedish National Library released a Swedish BERT model, which they have shown performs pretty well on the name, density recognition, and classification task on other types of data, but still no experiments have been made with clinical text. So this leads us to our research question, which is, can we improve recall on name, density recognition, and classification in Swedish electronic patient records by fine-tuning a pre-trained BERT model with domain-specific data without sacrificing precision? So the BERT models that we used in the study are first the multilingual model released by Google Research in 2018. This model implements the BERT-based architecture, and it's been trained on Wikipedia articles in 104 languages, including Swedish. The second model we used is this Swedish National Library BERT model, which also implements the BERT-based architecture. And this model has been trained on various sources of Swedish text written between 1940 and 2019. These sources include Wikipedia articles also, as well as legal text, newspaper articles, and some other types of text. So wider spread in the training data here. So to be able to use a BERT model for a specific downstream task, it first needs to be fine-tuned for that specific task with domain-specific data. So we've loaded these two BERT models with a linear output layer on top of their hidden states output, and fitted this layer with 80% of our corpus, Stockholm EPR PHI corpus. And for each of these models, we actually loaded two instances of them, where one was fine-tuned with the original data and one was fine-tuned with the pseudonymized version of the same data. We really didn't spend much time in hyperparameter optimization. We found that the models performed best after 3 to 4 training epochs. So 3 for some of the models, 4 for some of the models. And of course, more details on this can be found in our paper. For evaluation, we used two test sets. Test set A is the remaining 20% of the Stockholm EPR-PHI corpus. And the second test set B, contains other parts of the same database that have also been annotated, but these patient records are in slightly different medical domains than those that are present in Stockholm EPR-PHI corpus. In the second data set, the records have been annotated in a slightly different way, so we were only able to use 5 of the 9 PHI classes here. And the purpose of having the second data set is to be able to evaluate whether the models manage to generalize to a slightly different domain in the records. Here we can see the results on test set A. The best results were achieved with the Swedish BERT model when fine-tuning it with the original data. The recall we see here is on the same level as the previously highest reported recall. It's actually almost exactly the same. But this time we achieved this recall without sacrificing precision, which we were really happy to see. We see that the results on the multilingual BERT model seem to follow the same trend, where the model fine-tuned with the original data performs better than the model fine-tuned with the pseudonymized data. Again, we really didn't spend that much time in optimizing these models, so we can't make any conclusions regarding how much better these two models, one of these two models is than the other, but we can say that both the Swedish model and the multilingual model seem to be able to perform this task for Swedish. And again, we see that the results for the models trained on the pseudonymized data are worse than those where we've trained on original data. However, the difference between these results is much smaller than what was previously reported. And the results on test set B, not as good, but still high enough to be able to say that the models have managed to generalize somewhat to be able to perform this task on a different domain, a different medical domain in the records. And again, here the best results were obtained with the Swedish BERT model. So our conclusions are that these models offer a similar recall as we have seen in previous experiments, but without having to sacrifice precision, which is very positive. We also see a better robustness to the difference between training data and test data. And here specifically, I'm talking about how the models trained on or fine-tuned on the pseudonymized data also performed pretty well on the original authentic patient records. And finally, we have seen that the Swedish language model outperforms the multilingual model in precision and in recall. So this was really all I had to say. Thank you for listening, and please ask me questions.